Okay, thank you. Good morning. So, in the previous talk, we heard about great results from satellite sensing, from moon seismology. This observation provided us with kind of the ground truth all the models have to account for. Here, what I'd like to propose you is a slightly different exercise and a complementary approach, starting from mineral physics constraint, in particular density and velocity measurement of iron and iron alloys. I will build up a model for the moon's core and try to see how this model deal with external constraints and known observables. So, providing of the previous presentation, my introduction will be quite short. The moon always attracted significant interest from the very early in the humankind to the modern space exploration era, as the closest planetary body to the Earth has been the target of the Apollo mission, and is still kind of a natural first step for all the space agencies that want to go to space. And as we heard extensively, it's still the object of many satellite sensing missions. Thanks to the Apollo mission and the Apollo Lunar Surface Experiment package, the moon is the only other planetary body beside the Earth for which we have extensive and multiple seismic observation. In spite of the limited number of seismometers and the limited seismographic extent, all the problem Raphael already mentioned, this gave us a quite good idea and very precious information on the reference structure of the moon's interior. However, seismic investigation of the deepest part of the lunar, and when I mean deepest and then structure below and under kilometer depth, remains very challenging. You already seen this two model, and there is so far, from a seismological point of view, there's only one single paper that put ahead the seismic detection of an inner and outer core. However, the seismic quality was not such to completely invert the model independently, and this model and this paper, starting from seismic observation, had to assume some mineral physics constraint, and in particular in their data, in their analysis, they assumed a solid inner core made of pure iron surrounded by a liquid outer core with 11 weight % sulfur. At that time, seismic mineral physics constraint may be not so tight, so what we went up doing, well, not only me, but of course more in general, was try to place tighter mineral physics constraint, in particular on density and sound velocity. Why this? Well, on a general ground, the link between seismic observation and geophysical model is provided by experimental calculation, probing density and velocity of candidate materials at pertinent pressure and temperature condition. So, iron and iron phase diagram. Well, by definition of telluric planets and telluric satellites, iron is the main constituent of the Earth's, of the telluric planetary cores and the moon core as well. However, differences in the bulk masses imply different pressure and temperature at the center of this body, which in turn reflect onto the liquid versus solid nature and on the stable crystalline phase. At the pressure and temperature condition of the Earth, the expected stable structure is the hexagonal closed packet or epsilon structure, while for smaller telluric bodies, telluric planets such as Mars or Mercury, and satellite, including Ganymede and the Moon, the present interest, focus of the present interest, the expected stable structure is the phase center cubic or gamma phase. It's only recently that combination of synchrotron-based X-ray diffraction technique and multi-anvil pressed allowed exploration of the phase diagram of iron in extensive way, in particular around the gamma phase. This, together with the thermodynamic constraint, metallurgy, phase relation, give us a quite good feeling and allow us to derive this volume versus pressure relation for different isotherm. And in particular, having the moon as focus, we do have a quite good coverage on the 5 to 6, 4 to 6 if you want, GPa range and temperature between 900 to 900 Kelvin. So we do have pressure, volume, temperature relation at a suitable moon condition. Out of this relation, we can go and have a first check on this recent seismic model. In particular, we can directly derive density. Even be conservative and keeping relatively large error bars, the best estimation from mineral physics point of view for pure iron gamma phase of density is 7.6 to 7.8 gram over cubic centimeter, which is somewhat below the 8 gram per cubic centimeter. This is a few percent difference, but for density it's significant. And what about velocity? Well, this is somewhat more trickier to measurement, as measurement, and call for more exotic technique you might be less familiar with, so I will briefly sketch you the idea how to get this result. The technique we used is inelastic X-ray scattering. This is a two-photon technique, photon in, photon out technique, where an X-ray photon of well-defined energy, momentum, and polarization is inelastically scattered by the sample to a different energy, momentum, and polarization. Now, given the energy and momentum conservation law, the difference between the outcoming and incoming energy and outcoming and incoming momentum are energy and momentum transferred to the system. Now, in the limit of exchange energy much smaller than incoming energy, which is the case for a phonon, we're looking at velocity of collective vibration, typical energy of the order of 10 millielectron volt, excited by X-rays of the order of 10 kiloelectron volt, the modulus of the momentum is essentially unchanged, and the only quantity giving the momentum transfers is the scattering angle theta. So from an experimental point of view, what we can do is get the X-ray on our sample and perform a direction analysis of the scattered phonon to get Q and an energy analysis to get E. So what is probed by this technique are the phonon dispersion curve. This is an example of a BCC vanadium at high pressure. So once working on single crystal, what we have are this relationship of how the energy vary in terms of the momentum for the different main crystallographic direction. This gives us access to a large variety of physical properties. Here we only want to focus on elasticity and sound velocity. So on this initial part, on the initial dispersion of the acoustic mode, either longitudinal or transverse mode, where by definition the sound velocity is proportional to the slope of the dispersion. So we can get the velocity of longitudinal mode, acoustic mode, so P waves and S waves. But once we are on single crystal, we can solve the all-independent element of the elastic tensor. Unfortunately, as often the case at high pressure, we have to work on a polycrystalline material. This either because single crystals are not available, or as in the case of iron, the phase transition prevents us to keep a single crystal across the phase transition. So working on a polycrystalline sample, we lose the directional information, and what is probed are the average properties of the aggregate. But now if we place in the limit of the analysis and the framework of Bohr, Karman, lattice dynamic theories, considering a first order interaction, the aggregate phonon dispersion is well described by a sign relation with two independent parameters, the compressional velocity with P, which is basically the initial slope of the dispersion, and Qmax, the value of the Q at which the dispersion flat up and gets the maximum value. So we performed inelastic X-ray scattering and X-ray diffraction experiment on both BCC, so body cubic center, and FCC, phase center cubic iron, up to 19 GPa and 1100 K. Given the time and the audience, I will not enter too much in technical detail. The measurement, if anybody's interested, please feel free to ask a question later on. I will only stress that the experiment has been performed at 15.8 kiloelectron volt, an energy resolution of 5.5 millielectron volt, momentum resolution is 0.25 nanometer minus 1, and the beam size was focused down to 12 by 7 micron. This allowed us to use diamond anvil cell as pressure generating device, and high temperature has been obtained by micro-machined platinum wire furnace, basically a just furnace wrapped down around the diamond. Temperature was measured by S-type thermocouple, and pressure by Ruby at ambient pressure and at ambient temperature at higher pressure using the known equation of state. And these are examples of the collected data. The raw excess data are here in this inset. spectra characterized by the big elastic, the very intense elastic contribution, and this small bump characteristic of the longitudinal acoustic, it's the signature of the longitudinal acoustic phonon of iron. So we constrain the dispersion in the first Brillouin zone, collecting 8 to 9 Q point between 4 and 12 nanometer minus 1, and then through this relation, this sin fit, we get an estimation of the compressional velocity with typical indetermination around 1%. Where at synchrotron, we are getting diffraction. This allows us exact phase determination, density determination as well, and from the compression curve, the pressure-volume relation, we can estimate the bulk modulus. And then combining the bulk modulus and the compressional velocity, we can estimate shear velocity as well. In this case, due to error propagation, the errors are more the order of 5 to 6%. And these are the data here plotted for both the BCC phase in blue and the FCC phase in purple, sound velocities, VP and VS as a function of density. So over the investigated pressure and temperature range, both BCC and FCC iron exhibit a linear evolution of pressure of velocity with density. The FCC phase is about 400 meters per second slower than the BCC phase, but most importantly, both phases are significantly more, have significantly higher velocity than what assumed, what's proposed in the Weber et al. Paper for the moon inner core. Now, this difference is 1,500 meters per second, about 25% at constant density, is something quite large. So the first natural question we need to ask is, what might be the origin of such discrepancy? The first things we have to consider are potential and harmonic effect at high temperature. Our measurements have been done around 1100 K. Moon temperature for the core, depending from the model, range from 1300 to 1900 Kelvin. Well, can this explain the 25% difference? One first thing to notice is that all results, the full square, are 1100 Kelvin, well compared with the inelastic neutron scattering result. These are ambient pressure at 1400 Kelvin, and as well compared with the result on iron-nickel alloy at 300 Kelvin. So it looks like that between 300 to 1400 Kelvin, there's not much temperature effect. Even the few studies, even some studies arguing in favor of an harmonic effect at this pressure range estimate that no more than 5% reduction in VP in the ACP phase and around 3% reduction in the BCC phase. So clearly, we're not in the right ballpark. Even the larger reduction in VP, but in this case a constant pressure, but still recently expected for pre-melting effect is quite below what we observed. Another potential origin of this difference might be the frequency. Seismometers, we've heard on the order of Hertz. Here we are measuring at terahertz. So this is something that we might start considering. It's quite complicated, and harmonicity is a tricky business. It depends on pressure and temperature condition, grain size, stress and strain. But in general, we can say that probably the effect is larger on VS than on VP, but even then, assuming some literature value for the seismic quality factor of the core around 100 and the frequency dependence alpha measured for alpha iron, we end up with an expected reduction of the order of a few percent. Once again, not compatible with 25% difference. Nickel, other light element, sure, this is something that you need to look at as well. We know that samples of moon are relatively rich in nickel. So we know that including nickel into iron alloy slightly affect the density at the same pressure. But once looking at this velocity versus density systematic, these are data con sample with 22 atom% nickel. We don't see significant effect on density. Light element. At pressure and temperature condition of the moon, metallurgy tell us we cannot put too much light element in the solid iron. Nonetheless, the effect of inclusion of light element may be significant. By definition of light element, will reduce the density at the same velocity. But once looking at velocity versus density, for instance, in here is the case for some silicon inclusion in the ACP phase or the BCC phase, the effect, even for small inclusion, is rather to increase the velocity with respect to pure iron, not on the other side. So I think that the sound velocity proposed for the Moon's inner core is incompatible with that of pure solid iron or any plausible solid or iron alloy. Nonetheless, as already stressed by Raphael in the previous talk, I will keep as a firm constraint, as firm solid evidence from the seismology as well from the lunar moment, the refinement of lunar moment inertia, the existence of a seismic reflector at the inner core boundary and the liquid nature for the outer core. At this point, the exercise I can propose you is to reanalyze the seismic result, fixing velocity and density on the base of our measurement. So let's start with the outer core. To have a liquid outer core at the pressure and temperature condition of the Moon, the iron-iron-sulfur system is the most likely possibility. Otherwise, it's very difficult to have a liquid metal stable at that thermodynamic condition. This is the FEFS phase diagram at 5 GPa. Now, if we want to have a solid core coexisting with the liquid, the amount of total sulfur needs to be below 37%, because otherwise the solid phase will be FES, which is less dense than the surrounding liquid. Further constraint on the amount of sulfur we might put in the outer core comes from temperature. If we assume, as done in many works, that a partial melt exists at the bottom of the mantle, that gives an estimate of temperature of at least 1650 Kelvin. Now, temperature at the inner core boundary is necessarily higher than that at the core mantle boundary, but the absence of the active lunar dynamo suggests a stratified subadiabatic liquid, so the difference might be not much. But still, if we use this as constraint, in order to have partial melting at core mantle boundary, temperature to be at least 1700 Kelvin, so the total amount of sulfur in the liquid core is brought below 20% and even further below for higher temperature. So for our modeling, we will assume a solid inner core made of pure gamma phase, pure iron. You see the diagram here, you don't put sulfur inside the solid phase, surrounded by the liquid outer core with a 10 to 20 atom% sulfur, for an inner core boundary at around 5 GPa and temperature between 1700 and 1900 Kelvin. This is a plot of density versus pressure for iron-sulfur alloy at 1900 Kelvin for various sulfur content. The big point, our recent experimental result, is X-ray diffraction on liquid compressed in a Paris Edinburgh press. The smaller symbol are older literature result, and this colored line is the outcome of the thermodynamic modeling. Here, the idea is to get a relation that gives us the density versus pressure as a function of sulfur content. Now, this is a modeling with some assumption, but as you can see, this model quite good grasp the entire picture and give us an idea of how density and change with pressure and temperature, and consequently velocity. For a liquid, the velocity is just the square root of the compression of its bulk modulus over density. The bulk modulus is something here in this line. So our best estimate, even to play safe and keep quite large error bar, is for a density for the outer core between 6,500 to 7,000 kilogram over cubic meter, and the corresponding velocity between 3,600 to 4,000 meters per second. For the inner core, we will start from our result on a solid gamma phase at 1100 Kelvin. I would not say that the temperature effect might be so large, but still, to play safe, I will include, for our estimate, at least within the error bar, a reduction up to 5% in VP and 10% in VS, moving from the 1100 Kelvin up to 1900 Kelvin. And if I correct accordingly this result, the best estimate we get for the inner core is a density between 7,600 meter per kilogram over cubic meter and 3,800, a VP between 4,700 to 5,700 meter per second, and VS between 2,100 and 2,400 meter per second. And this is a cartoon summarizing our result. VP in blue, VS in green, and the density rho in black. This part here is assumed by the Weber et al. Paper. Now, having the density and the velocity, we can go back to the seismic observation, in particular the travel time, and impose our velocity in the outer core and refine the position of the inner core boundary, getting an inner core around 250 kilometers in diameter, surrounded by, no, this is not diameter, this is radius, sorry, surrounded by 80 to 85 kilometer thick outer core. As I told you at the beginning, we can directly compute the density, the mass, the overall moon mass, the moon moment of inertia, the central moment of inertia, getting an agreement within 0.1% of known values. So it looks like that so far this model might be standing. Other consequence out of this model we can discuss on the sulfur content across the entire core as a simple mass balance between the sulfur-bearing outer core and the pure iron inner core. We get an estimate of total sulfur in the core between 3 to 6 weight%, which looks quite in good agreement with the recent independent constraint on the total sulfur amount in the moon. Lunar core formation model together with the metal silicate partition and siderophile element indicate up to 6 weight% sulfur in the core, in the moon core, while modeling of the history of the long-lived, now extinct lunar diamond might call for 6 to 8 weight% sulfur. So independent constraint tend to push that sulfur might do the job in a reasonable amount. Okay, so here again I'm putting these things up. I'm not pretending to tell you the reality. This is not clearly the moon. This is a model, but I think it's a good indication. Is a mineral physics constrained model that might act as a base to build up further complexity. I will also stress that these experiments are quite cheaper than most of the things we heard before. So, how keep improving? This brings to the outlook. Some velocity measurement on solids, we'd like to be able to probe the same, do the same exercise we did at 1100 Kelvin at higher temperature. To do that, we need to move from resistive heating to laser heating. That comes with some experimental challenge we might have to take, but hopefully in the years to come, we will be able to do that so that we don't have to extrapolate or take assumption on temperature effect. The sound velocity measurement in liquid, this is another thing that is coming up quite well recently. These are two independent study ultrasonic measurement in Japan and the United States on sulfur-bearing liquid. This gives us a quite good feeling. We use that in our thermodynamic as constraint for our thermodynamical model. However, for technical reason, all these samples are quite sulfur-rich. So we would like to repeat this kind of measurement on sample with more realistic sulfur content. Beside mineral physics, clearly there is a lot of interplay between this kind of measurement and other geophysical or spatial observation. For instance, here we refined the radius core using the seismic constraint, the seismic travel time. Another way to do this is using the refined number from tidal dissipation or log number, as well moment of inertia, fixing the density to the mineral physics constraint and leaving the dimension of the core as a free parameter to fit the log number, for instance, or in the moment of inertia. Temperature is something that we assumed partial melting at the bottom of the mantle. We heard before that that might not necessarily be the case. Assuming the partial melting at the bottom of the mantle force our model towards the higher pressure, higher temperature. We are proposing a 17 to 1900 Kelvin in the moon. Classical older results were more around 1300. Having a colder moon imply having a more silicon-rich outer core, but as well as a thinner outer core. So the two might compensate in terms of total sulfur content, but the physical properties might be affected by more or less sulfur content, more or less temperature. This is something where having independent constraint on core temperature might be quite good to plug in for our modeling. And definitely setting like this meeting provide a great ground for exchange. People with different background, different discipline, start to interact and define future direction, future collaboration. That would be great. Finally, I couldn't resist to the temptation to extrapolate or a result up to the condition, of course, up to Mars size. If we do this just linear extrapolation, pure gamma iron at 42 GPa and 2500 Kelvin, this few number I picked in literature as indicative of the expected condition at the center of Mars. So this is the corresponding density. Have the velocity of VP around 7100 meters per second and shear velocity between 3600 to 4400 meters per second. Now we don't have seismic observation for Mars yet, but the main objective of the InSight NASA Discovery mission, whose launch is expected in March 2016, is to place seismometers on Mars. So such kind of observation, similar studies might not only work as a predictive, as a kind of predictive power, but as well as help interpretation of seismic observation. And just let me conclude acknowledging the closest collaborator for this study, Guillaume Morar, Guillaume Fiquet at UPMC, Nick Schmer at the University of Maryland, Tetsuko Babayashi now in Edinburgh, Michael Krish at TSRF, Fay at Geophysical Lab, and two funding agencies. Thank you.